Okay. Gotta switch to English for the recording. Welcome, everyone. So it looks like we're going to have this lecture and one more lecture about logic next time. And then after that, we're going to hopefully already next week, we will start selecting projects, class projects. And then after that, once you know what your class projects are, we're going to switch to a more personal mode of working where you're working, I think most of you probably in groups of 2. And then you just meet one-on-one either with Daniel or with me. So somebody's going to oversee your project and then we have meetings. There will very likely be some extra lectures where we're going to discuss something that many projects need to know, and then we're just going to focus on a particular topic like that. And but I invite everybody, of course, to come to these special topic lectures because they will be generally useful, and you learn, you see what's out there. So even though maybe you're not using it, it's still good to see these things. Okay, so far we have been doing types and dependent types and equality, and last time we were talking about sums and records, and today we're going to look at how records are used to do a kind of structured programming and structured mathematics. So there are 3 examples that I'm going to discuss. One is how to use records and dependent types for data structures, and we're going to look at the dictionary as a data structure. It's a very simple data structure. Then for mathematics, we're going to scratch the surface by looking at monoids. So monoids are like groups, but you don't require inverses, right? And then the third example is kind of a mix of the two to give you some feel for the abstraction, how abstraction enters into computation, and we're going to look at monads. So monads are a mathematical structure that can be used to describe computational effects of all sorts. And I think also generally as part of this course, it's good that you learn about this. So this is not just about formalization, this is also about learning, well, in the case of dictionaries, how to not just specify a data structure, but also its correctness. In the second one is how to formalize mathematics. And the third one is there's also this other component of how to use mathematical abstraction to describe a phenomenon in computer science, which is computational effects. But before we do that, let's just sort of have a little overview of Agda modules, because we are going to increasingly use Agda modules in more complicated ways, and they can be really helpful for organizing things, and so it's good that we know about them. So of course you must have learned by now that when you want something from the Agda standard library, what you do is you import them, and notice that here I'm somewhat more careful. I'm not just opening and importing. So the ones that I'm going to use throughout, I do with an open import, so they will be just the contents of the module is available throughout the file. But some of them I'm just importing, which means that if I want something from data list, I have to type data.list. Yes. But what you will see later is that in the submodules, you can open one of them, and then it's open just there. It gets crazy if you open everything, then things clash, because there are name clashes, it becomes horrible, okay? So we're going to practice opening things locally when needed. Right, so this is, I think this I just copied from Daniel. He also likes to be very specific about what gets imported. You can say instead of, so see here, I'm just importing everything that's in here. But here, for instance, this line here will import only this stuff and nothing else. So you can just selectively import some of the things. And that's also good discipline. In general, you don't want to have a gazillion things in your context that you could use, because then eventually it gets hard to figure out what's going on. Although if you have a good IDE, it's usually often not a problem. Okay, so one thing that you should probably have noticed also by now, but let me just say a few words about this, is that modules can be nested. So you can have a module, By the way, this is already a nested module because there is a top module, see here, okay? So already foo is nested. So, but if we ignore that fact, bar is a submodule of foo. So bar goes from here to here. Actually, no, it just goes from here to here. All of it is just a submodule. I just wanted to demonstrate that you can have a module inside the module. And this is actually useful. And now from the outside, you can get to something that's in the submodule in several ways. You could, this is called a fully qualified name, so you just exactly write down what you want. You could open the outer module, and then in that case you can get to this cow by saying bar.cow, or you could actually open the inner module and then it's just cow. I think this is clear, right? And also, there are private blocks that you can use. If you put something in a private block, like here I put bull and chicken in private blocks, they can be used inside the module here, but they are invisible outside of the module. You can't get to them. And this is just basics of good programming, right? So your programming discipline as a programmer should be that you only expose the things that need to be exposed. Otherwise, you will suffer later when you try to modify the code, because if everything gets you, if every piece of code can refer every other piece of code, whenever you change anything, you have to worry about all of the rest of the code. So that's not a good strategy. Modules can be anonymous. So if you give a module the name underscore, that means that the module is not really there, but it's still there as a unit of organization to bunch things together. And this is quite useful. So for instance, suppose I have two definitions and they both use data list. And they both have they both share some private definitions. Then I could do multiple open data lists once per function, but it's easier to do it as follows. I just create an anonymous module, and then I open something in this module, and I do other private things, and then I put these foo and bar that need to use this stuff, I put them in the module. And then once I'm outside, so this one is now outside, this open data list is not valid anymore, like it's not there, the private stuff is gone, but foo and bar are there. Because this was, if I name this module, like up here, if I name this module, then I would have to refer to foo and bar by the module name, but because it's anonymous, it just goes through, okay? So you can just say bar here, and it'll go directly here to this place. You don't say underscore bar or anything funny like that. This really means the module name is not there. Modules can be parameterized. By the way, this is blue because that's meant for you to learn to read the documentation. There really isn't that much documentation, right? So this is the documentation of the module system. What is this? This is like one coffee, right? Worth of reading. So where were we? Here. You can have a module. Now we're coming to things which you may or may have not seen in other programming languages. So a module can have parameters. So here's a module that has one parameter, which is a number. And then this number can just simply be used inside the module, like for instance, n+7. The way to think about it is that rabbit is not really a module, it's a function from numbers to modules. So in particular, anything that's inside the module expects this number. So now there will be several ways to use this tail. So let's look at them. So you could, first of all, you could just say, you could have a fully qualified name. So if you say rabbit.tail, well, rabbit.tail wants a number. You have to say what this n is. And so once you give it the n, then you will get here number 9. So this will be number 9, and this will be number 8. Yes? This is without opening anything. You can also open the module and give the number. So now this is going to open the contents of this module, and the number will be fixed and will be 100 everywhere. So now I just write tail. Tail doesn't need the number anymore because it was already supplied here. So now I just write tail, and it's 107. And then there is the middle ground where I open the module, but I don't specify the number. So now I can write tail. I don't have to write rabbit tail, but because the number was not specified here, down here, I still have to supply it. So which of these use cases happens depends entirely on what you're doing. Sometimes you want to open the module with some fixed data, because throughout it's going to be the fixed one. But sometimes you don't do that. You want to vary it, in which case you probably do something like this, and then you can vary the parameters. Questions? So this is used for organizing larger units of software, right? So what is this like? So this is a little bit, so first of all, modules are a bit like classes in Java, or maybe something like type classes in Haskell, and Haskell also has modules, so there's a difference. So Haskell modules are a little bit like this. In OCaml, there are actual modules and functors which are like this. In Python, every file is, do they call it a module? What they call it, a package? I don't remember. I think it's maybe a package. Package, right? So most languages provide some shape or form for organizing units of software, of code, and modules are like that. Now, what are the parameterized modules like this? What's that? Well, in Java, this would be most closest to generics, where you have a generic class that depends on some other data. In OCaml, this would be actual functors, because they are maps from modules to modules. But so in Python, you wouldn't. Python is kind of crazy, so there's probably a way of doing this, but it doesn't support it directly. None of them are as flexible as what Agda does, because Agda has dependent types and sets and universes and whatnot, and so you can do this sort of on a large scale. Okay, one neat way is to have a parameterized anonymous module. So let's have a look at that. So consider the following module, which just has 3 functions. Okay, the only point for these functions is that one thing keeps repeating. You see, every one of them takes some universe level L, and then a set A at that level, and then it does something. See, it keeps repeating here. And you will notice that in the code that we have had so far, there is a lot of such repetitions. This can get a bit annoying, because often the meaning of these is always the same, and you just keep repeating them. Okay. So what you can do instead is you do the following: you take out these arguments, and you create a parameterized module, but you make it anonymous, and then you have these 2 arguments here. So now what happens is that each one of them will inherit these arguments. So they will be common, like each one of them will have these arguments there. And so now this is a good way of creating several functions which share some of the arguments in common, and it's also more readable. So a typical use, this is a stupid use, but a typical use would be, suppose we have, like you want to say, suppose we have a monoid. Well, then we're going to define 25 functions. Instead of giving each function a monoid as an argument, you create an anonymous module at the beginning, and the way you read this is, now we're going to do a unit of work. And let's assume that we have this stuff here, then we work with it. So it becomes nicer. You don't have to keep repeating the arguments.
Sorry,
yes?
just a clarification. So I don't need to refer to this anonymous module?
No, this just goes through. Yeah, it will. Yeah, whenever the name of the module is underscore, that just means that it will just automatically fall through. You cannot refer to it. Yes. Not only you don't have to, you cannot refer to it. It's not really there. It's a mirage. Yes. There is a lot of design space in how you organize stuff like modules. You know, is it type classes? Is it classes? Is it modules? Is it one profile? Can you have submodules? Can you have parameters? What kind of parameters you have? This is a whole area of programming languages, and what we are observing is one particular selection of choices, which I think works really well. I like the Agda modules. They're nice. They're less heavyweight than, say, OCaml modules. And I'm not going to comment on Java, where everything is a class. Okay. There's there are other things that you can do with modules, which you can probably learn by osmosis, by observing what we do. Namely, you can rename a module when you import it. You can rename specific things, and we will see example of this. You can be very selective about what you import, and you can also hide things when you import. I'll let you, oh, there's one broken link here that I need to fix. Okay. Okay, let's get to the main stuff. Let's do records. Okay, let's use them for something. So the first one is going to be dictionaries. So let's repeat what a dictionary is. You have probably seen dictionaries before. As a data structure, what is a dictionary as usually understood by a data structure? It goes by other names like associative list, associative array, but essentially the point of it is that we have some keys, and these keys are mapped to some values, and we would like to manipulate this mapping. And often, I mean, normally dictionaries are finite, so we have finitely many keys. Okay, so finite maps. That's what the functionality is. More or less, it's a map from keys to values. But now we also have to discuss what can we do with them, and then also how might you implement them. So what are some basic operations? Well, first of all, we can have an empty dictionary that doesn't have any keys. So if you try to look anything up, you are not going to find it. And then you can have something which adds, oh well, a lookup is one of them. And I went by Daniel's naming conventions for dictionaries. So he's a true hacker, so everything is a 3-letter thing. Okay, so empty dictionary is emp. And then you can look up. So how would the lookup look? So if I have it, so this is called LKP in the code. So how does the lookup work? So you have a dictionary D, and think of this as something that maps keys to values. So you give it then you give it, so this is a dictionary. Then you give it a key, and you want to know what the lookup value is. So out of here, what can come out? Well, out comes a value, right? But not really, because it may be missing. So it's an optional value. And we've already seen this. How do you do this? Well, you either have, say, just and some value, or you say nothing. You use the maybe type, which has these two alternatives. So this is going to be mapping so lookup takes a dictionary, a key, and then returns an optional value. And then we also want something that updates a dictionary. Now here, there are essentially two styles. One style is that your data structure is stateful. A stateful data structure, which is typically embodied by object-oriented. Object-oriented programming is often is a kind of organizing stateful data. The idea is that I actually change the dictionary when I update it. So if I add a new key-value pair, the dictionary will change. The other one is more of a functional thing, where I take a dictionary, I take a new key and a new value, and I want to update this. I update. So the function in the code is called add, and what I get out is a new dictionary. So the old dictionary didn't change. You just get a new dictionary. Now, this sounds crazy at first, especially if you are used to stateful programming, because who is crazy enough, like, are we really going to make lots of copies of a dictionary, right? But as it turns out, this approach actually works really well when this dictionary is something like a tree. When you're updating it, it'll share most of the tree with the previous copy. If your data structures are immutable, then you can share them at will, because nothing can go wrong. And in fact, this is a good approach. It turns out it's more difficult to think about stateful data structure. Programmers find it can be quite tricky, and you can make some nasty mistakes when you have, for instance, stateful data structures that share pieces. Then it gets really nasty. So this does not mean that it's inefficient. It usually means that the new dictionary is slightly different from the old one. And they share, in memory, they actually share lots of data. So it's not such a crazy idea. So this is what a dictionary, how you would describe a dictionary to a programmer. And then if you want to code this, let's see how are we going to code this. We actually have to start reading up here. So first of all, there is one important bit, which is we have to think about these keys. If you're going to look up things and insert new keys, then there is something you need to know about the keys. If you know nothing about the keys, it's going to be impossible to implement this in a reasonable way. What we need to be able to do is we need to be able to compare keys algorithmically. If you cannot compare them for equality, then you're going to have a problem. In a real data structure, actually, you will actually want them to be linearly ordered. So for good implementations of dictionaries, will require either that you can hash the keys, right? Or that you have a total linear order so that you can make balanced search trees and so on. We're going to keep things simple and say, well, what's the minimum we need? Well, the minimum is that I need to be able to compare keys for equality, because otherwise it's going to be really difficult to do an update. If I already have a pre-existing dictionary and I want to update one of the keys, I have to be able to tell which one to update. So if I can't even compare them, that's a problem. Now you might be thinking that you can compare everything in this world, but that's not the case, because the keys could be, for instance, functions from natural numbers to natural numbers. It's kind of difficult to compare functions from natural numbers to natural numbers. It's not decidable. Okay, so what we need is an assumption that keys have decidable equality, and this is something we did the last time.
Sorry?
Yes? We will do just the equality. We will just do decidable equality, but what else did you have in mind? That you might want something? Order, yeah. You would want ordering to have a reasonable implementation of dictionaries that actually works in nonlinear time. You would need something like ordering. We will be able to achieve linear time with this assumption. Yeah. It's an interesting theoretical question to give a data structure which has decidable equality, but you can't give a total order. What would that be? Yes, what would that be? So, we need to assume that keys have decidable equality. And that's just another example of a little structure. So we're going to have a little record type. What is a key? Well, a key is a set, so a set of keys, plus a testing function, which, given k and k prime, decides whether they're equal. Now, equipped with this, we can go and we attack the actual definition. So what is a dictionary? Now we are, so careful, we are now giving the type of dictionaries. Once we're done, we will not have any dictionary at all. We still have to implement it. So to give one element of the type dictionary will be to implement dictionaries in some specific way. So that will be an entire implementation of dictionaries is one element of this. And one single dictionary will be one element of this type down here. Okay, so let's not get confused about that. Okay, so the inputs, it's a parameterized module because we want to implement dictionaries with respect to any kind of keys and any kind of values. So the keys will come from from the record key, K, and then the values will be in A. And there are universe levels here that you can entertain yourself with, but I'm not going to get into that now. Okay, so what are the fields? The fields that we discussed were this. Well, first of all, you need the type of dictionaries. There's a carrier type. So one element of this is a single dictionary. So it could be some sort of a list of pairs or something like that. Or maybe it's some sort of a tree, search tree, who knows. And then there is going to be a value that represents the empty dictionary. Then there is lookup. So a lookup, it takes a dictionary and a key, and then it maybe gives you a value. And then there is the update. How does the update work? It takes a dictionary, then it takes a pair, a key and a value, and returns the updated dictionary. This is how much you would expect in a programming language. But we can go on. We can do something much better. We can actually write down the specification. We can write down equations because we have dependent types. We can keep going. And our data structure will also contain requirements on how this stuff behaves. So let's have a look at them. So this one says that if you look up anything in the empty dictionary, you will get nothing. This is what is specifying emp. This is saying emp is really empty. Okay, so what does this one say? This one says if you look up, okay, so if I take a dictionary and I update it so that k maps to x, and then I look up k, what do I get? Well, presumably I get x. Yes? And then there is one more, which is what happens if I update with some other key. So if the keys k and k prime are different, and I update k to map to x, then I look up k prime. What result do I expect? I expect the same result as in the previous dictionary. I didn't break the other keys. Now this is neat. What does this mean? This means that when you implement the dictionary, Agda will want you to prove this stuff here. So it will be impossible to implement unreasonable dictionaries. Implementation comes with the proof of correctness. I discussed this before. Is this the future of programming? Blah, blah, blah. I think it is going to be increasingly important to have the ability to do such things in programming languages. But as you will learn the hard way in this course when you do your class project, it's really painful and it takes a lot of time, at least with the existing tools. But you can look forward to the tools you will be using in 30 years' time, and then you will be explaining, oh yeah, I did this when I was young. But we had to do it with our bare hands. Okay, so one other thing that's worth noting is that when you have a structure like a dictionary, you can have some basic functionality. This is the basic functionality. But out of this basic functionality, you can build more stuff. For instance, this add thing will always, it doesn't say what it's going to do exactly, but it looks like if I reinsert the same key into the dictionary, it might actually change it. But maybe this is not necessary. Or sometimes you want to have a different update function. You may want to have an update function add, which only adds a key value if it's not already there, and otherwise it doesn't do anything. But we can implement it using this stuff here. So let's do that. But where would you put the extra functionality that you can derive from the basic functionality? Where would you put it? Well, normally you would put it in the same module, in the same class, in the same unit of whatever you're working with. So this is the case here as well. A record is also a module. So we can put inside of it not just the fields, but arbitrary definitions. So I will continue this record. If you look carefully at how this is indented, 4 levels means I'm still inside the record. So down here I have some additional functionality. What does this functionality do? It says add a key value pair only if the key is not there yet. So how would you do that? Okay, so you say I take a dictionary, I take a key value pair, and now I need to test. So what I do is I first look up the key in the dictionary, and if there was a result, I return the same dictionary, otherwise I update. And this is also quite useful to have this ability to define auxiliary stuff. Also auxiliary theorems and auxiliary, right? Not just functions, lemmas. How are we going to implement this? You're going to work in the exercises to implement this using lists, but we are going to do it in the silliest way possible, which is, well, a dictionary is supposed to be a map. So how about if we just make it into a map? Why not? So I will actually say dictionaries as maps. So how do I think of a dictionary? Well, it should go from keys to values, but not really to values, but remember to maybe values, because maybe if a key is not present, I still need to be able to look it up. So that should be my dictionaries. That is the most straightforward way of defining them. Now, is that a good idea? Actually, as it turns out, it's not a terribly good idea, because when you update a function like this, you're just covering the previous definition with some new stuff, And so as you're updating, your function code is growing, and it's never getting smaller. So in practice, you wouldn't do this. In practice, the reason why you want dictionaries to be implemented as trees or as lists is both for efficiency purposes. If you have a nice data structures, the operations can be logarithmic in time, logarithmic in size, but also because you want to control the size. You actually want to be able to make them smaller. Nevertheless, just as an exercise, let's implement this. And why is this not colored the way I want it to be colored? There we go. So now we're going to implement one kind of dictionaries. Also, let's pay attention to how I'm using this. I'm going to say, start a new section. I'm working on something. Assume that we have keys and values, the data type of keys and the data type of values. I'm opening the dictionary. Dictionary is defined to be a record, but because it's also a module, I can open it, and then I gain direct access to all this stuff that's in here. I don't have to keep writing dictionary dot. So I open them, and here is a little auxiliary function which updates a map. So if I have any map, if I have a map from keys to any type X, it doesn't have to be the values, any type X. So in reality, I'm interested in the case where X equals option A, but I'm doing this slightly more. And I give it, I say, please change this map so that this key maps to this value, and give me the new map here. I have a map here. It might actually be better to call this F, like this. So I have a map F, and I want it to change it, update it, so that K maps to X. And then what will be the result? Well, the result will be a new map, which will look up some K prime. How will the new map look up K prime? It will first test K and K prime. If they're equal, it returns X. Otherwise, it consults the previous map. And now I'm going to implement dictionaries. Once again, I'm not implementing one dictionary. This is a particular concrete implementation of the abstract interface dictionary. Dictionary describes what needs to be done to implement dictionaries, and I'm going to do one of them, one particular way. And here is where you see the crux of the matter, which is that a dictionary is represented simply as a map from keys to optional values. What is the empty dictionary? Well, which map represents the empty dictionary? It's the map that always returns nothing, because there shouldn't be anything in it. Okay, how do I look up? Well, I look up by applying the map. That's the whole point. I'm trying to make lookup as easy as possible, so it's just, you don't have to do anything. In fact, the way this is written, it's equivalent to this. It's just the lookup is identity, right? I don't have to say, take a dictionary, and then when you get an argument, apply dictionary to the argument. I don't have to do that. Okay, how do I add? Well, I add with this update key map, which we looked at. I just say update D so that K maps to just X. And now we need to prove the three properties. One of them is easy. So let me just show you how this goes. So you will get to here in Agda. Well, this is function. Okay, up to here, this is functional programming. This is just Haskell. Okay, this would look exactly the same in Haskell. So now we get to the actually satisfying the conditions. I look at the goal and I say, oh, what is this? Okay, for any key, I have to prove that nothing equals nothing. That's probably going to be easy. So Agda is already telling me what needs to be done because it knows that empty is the function that is doing nothing. So it's already simplified the goal for me, but that's what you need to prove to show that I correctly implemented the empty dictionary. So I do refine, and then here I do Control-C, Control-A, and it says, yeah, this is REFL. Then I see that K is not needed. I make it anonymous. I'm done. These other guys are more complicated. And when you get into a slightly more complicated situation, the way I usually implement this is like this. I'm at a point where I'm trying to implement something complicated. What I do is I say, oh, I will need an auxiliary function. So I go down here and I say, I will need an auxiliary function. And I put question marks everywhere. I don't know what its type is. I don't know what its implementation is. But I do know I want to use it here. And then I tell Agda, this is the answer. And Agda says, OK, But now Agda knows what the type is because it knows what type it wants here. So I can go to this hole and say, hey Agda, what is this? And Agda says it's that. So sometimes it gives you something crazy and you need to clean it up a little bit, but you get an answer, it's doable. And then you go and you implement it. So this is exactly how I implemented this thing here, but I didn't call things foo and bar. So this is actually that. Let's have a look. What's the timing? I think we can do this. Let me just see. Yeah, we should probably. Okay, so let's do one of them. On a larger screen, this looks better. So if I need to break the line, I usually break it down so that the conclusion is on the line, on the line of its own. So what does this say? This says if you update D so that K maps just to just X, and then you look up K, you will get just X. Yes? How is this? How does one do this? Well, you would start. Daniel always tells me you shouldn't be showing them the solution because that's confusing. Okay, so there, no solution. So I will do this thing. Okay, and I'll say I want a key, I want a value, I want a what? Keys X, I want a dictionary, and then I need to prove something. And then I stare at this and I say, okay, so, but how do I prove this? Any ideas? So I normalize, say, okay. So I press Control U, Control U, C, well, this is Control U, Control U, C, comma, everything with Control U, Control U. No, sorry. There, that's the one. Control U, Control U, C, comma. Okay, so once I see that this got, you see, it unfolded the definition, and it says, well, the result of this depends really on what this test is doing here. Okay, so when it depends on the test, I know that I need to test the keys. Yes. I say, how about if we test the keys? Sorry. Okay. How about we test the keys? So this is the construct where you additionally say, I am additionally pattern matching on the result of some other call. And they say, well, please do this. And then I say, what are the two possibilities for P? And it says the two possibilities for P are, yes, well, I don't like this. I'll just call this P, probably is better. So I look and I say, it wants me to show that this thing here equals just X. What is P? P is the proof that K equals K. Okay? So what I can do, I can further say, please consider what P could be. And it says P has to be reflexivity. And now, if I ask what happened now, see, it simplifies. The unsimplified says yes of refl, but the definition of update key map says that when this thing is yes, then it can further simplify, which is why here it knows that this is just X, just X. This one, what do I do with this one? I am supposed to show that D of K equals just, and the assumption I have is that K is not equal to K. So this case cannot actually happen. This case can't happen. How do I say this can't happen? I say bottom elimination. I say I'm going to, this follows because anything follows from false. And then Agda says, yeah, you think this follows from false? Okay, but now you have to prove false. And then I say, well, but I can because I have a weird assumption. So I say this is P of refl. And now I have the solution. So when the case cannot happen, you have to have reason why it cannot happen, and then you say it couldn't have happened. The other one is quite similar, except it's the other way around. So I'm not going to go through it, but it would probably be polite to have slightly better line breaks. Okay. Now here's the thing that sometimes happens, which is that you have your data structure, like a basic dictionary, and then you want to improve it a little bit. So you would want to reuse the functionality that you already had without copying it. Is there a way of doing that? Well, in object-oriented programming, that's inheritance. One class inherits from another, you copy it in. What could you do? What can you do here? Well, there are several mechanisms that you could use, but I'm just going to discuss the most obvious one. The most obvious one is that if you want to have sort of an upgraded dictionary that says, for instance, that has an additional equation, so here's an additional equation. This is also a reasonable equation. What does it say? It says, if I update my dictionary so that k maps to x, and then I immediately update it again so that k maps to x prime. The first update was kind of ridiculous, right? If I update k maps to x, then immediately override it with k maps to x prime, that should be the same as updating just once. So if you want to have this additional equation, what are your options? Well, I could just change the old definition, of course. But suppose I want to reuse this. One option is that I do the following. I define a new map, I define a new record, which has a very unimaginative name here, dictionary prime. And then what you do is it has a field that is essentially the old structure, plus a little bit of new stuff here. Notice that I can open the old structure. So this is instructive. How do I get access to this guy here? So instead of just saying open dictionary, if I say open dictionary dict prime, so I give the record type, I give it one instance of it. When I open this add and lookup and so on and keys, they will all be from this particular dictionary here. And then I just state it. So this is a way of doing it inheritance, sort of a little bit by hand, very explicitly, but the open statement allows me to do it in a painless way. When I open, I just get access to everything that was in the old one. So it really is, it's going to feel like you're just inheriting, so it's not so painful. And then here is the partial maps that this is the partial map dictionary primed. So how do we implement this one? Well, we have to implement a record. It has to have two fields. The old one is just the old implementation, this one. And then I need to prove the new equation, which I do. Now, I'm going to take you through this definition because it's important to understand how I prove this. But we'll do that after we will do this after the break. Because this one is a little tricky. Where are we? We are in a random spot. We really are in a random spot. Okay, so down here, when we want to update this, there is trickiness to showing that partial maps satisfy the additional condition. So we will discuss this. But let's have a break now. So it's 5, so until 20 past. So here we have a little piece of tricky code, and I think this is probably by most Agda users considered to be already somewhat advanced to know how to do this stuff. So let's see if I can pull it off without looking. So to remember what we were doing before the break, the idea was that we want to prove an additional property of dictionaries. And the additional property is written here. Namely, if I update the key k with x and then I immediately update it with x prime, that's the same as updating it just with x prime. Okay, so how do we do this? Okay, you write down this question mark, you get a hole, and you stare at it. And the first thing that I usually do is I look at the arguments And I say, oh, okay, so this thing, I could look either up here or down here or up here, it's the same thing. And I say, oh, this thing actually wants a k and an x and an x prime and a d. Okay, so now how am I going to prove this? I first look at the normalized goal, so that's Control U, Control U, Control C, Control comma. And it looks horrible. But the important thing to note is, why does it look horrible? Why doesn't it compute? And it doesn't compute because it has these tests here, you see? It's a test. And these tests came out of update key map, which was defined up here, which tested the two keys for equality, and it said there are two cases. So until it knows what case it is in, it won't compute. So in order to compute, it has to figure this out. Okay, good. So how will it figure this out? Well, the way to figure it out is to perform the test here as well. So what am I testing? I'm testing, again. Yes, so I'm testing. I have to look a little deeper. I have to ask myself, what am I comparing even? I'm comparing two partial maps. How am I going to prove that two maps? See, this is a map. These are two dictionaries that I'm comparing. So I'm claiming that the two maps are equal. But in Agda, we had equality last time. In Agda, equality of functions is a nasty thing. Because Agda, as far as it's concerned, functions are just some pieces of code. So two different pieces of code that compute the same thing are not necessarily the same function. So I need to use function extensionality, just like we did the other day. So we're going to now, the first step is going to be to reduce this to saying, we're going to use function extensionality so that instead of proving that the functions are equal, we will instead prove that for every k prime, the results are equal. So that's function extensionality, which is presumably up here somewhere. See? I imported the statement of function extensionality from the standard library, and then I postulated it. I said, it's true, without explaining what it is. So this funxt, if I look at it, funxt, what does it say? It says, well, it says this, which is kind of boring. It says something. It says, to show that two functions are equal, you have to show that they give the same results. So I can use this. And when I use this, now it says, oh, okay, so now you have another key and then something, okay, but I see now that at least I am doing that, I'm doing the following. For every key, which is unfortunately called x1, this equals that. So now I know that what I need to do here is some sort of an additional lemma. So I'm going to do my trick where I say, oh, this I will do separately. This is too much, okay? So I go and I look at, I say this. And I say, please, I will do this here. And then I go here and I tell Agda, Control C, Control S. And Agda says, yeah, this is what you need to prove. I don't like this x1, so I will replace it with a, what would be a good thing to replace it with? K prime, probably, because this is a key. And so now I look at this statement to see if I understand it. So now it's saying for every K prime, you have to show me that what? If I add here and then I look, did I confuse myself? Yes, it'll be the same thing. Yeah, it's okay. If I update D so that K maps to X, and I immediately update so that it maps to X prime, and then I look up some arbitrary key K prime, then it'll be the same as updating just the last time, just the last one. Okay, so now I have to show that this works for all K primes. So I go here and I say, okay, for all K primes, what do I need to do? And I normalize again, and I see now that I have the test key things. Now I actually have it here, you see? Before it was under lambda, so I couldn't do much. But now it's outside of lambda, so I can do it. It's not under the definition of a function. So I say, okay, so let us test keys. I say with test keys kk prime. And then I say, I know that I'm going to get an extra result, let's call it P, without this equal time. And I reload, and it says, yep, what is P? P is the decision whether they're equal. And then I say, well, but what could the P be cases? And it says there are two possible cases, and because I don't know what's going on, I call them X. And I say, well, this is not very nice, let's call them P. I need to reload. Okay. This one now computed. So what just happened? Because this is the case where the test keys computes to yes, it could further compute that the goal is just that. And so this is reflexivity. Okay, how about the other one? The other one, here, we want to show this, and I say, how does this normalize? And I look at the normalized goal, so computed goal. No. S, okay. So the other one is now, seems a little bit strange because it should have computed, but it didn't, all right? Why didn't it compute? You see, I tested for k and k prime, but somehow, miraculously, this test kk prime didn't want to compute. So what is going on? To understand what is going on, I will go for a moment back to before I did the testing bit to carefully look at what is happening to show you. Look, on this side, that's the side that is computing, there is just exactly an update with a test key. And this one is computing. But the other side has an update with a test thingy. But then there is a further one in here, you see? There's another one in here. And that one is under a function. So that's the one that doesn't want to compute. Because Agda says, well, I don't know what to do about that. You ask me to compute with k and k prime. We're testing the k and k prime. So it's not going to simplify this one. Only later does it find out that if it computed all the way slightly more, it would again get the same test. But it's too late for Agda at that point. It's already did its work. So now we're kind of stuck. We calculated, but it didn't calculate all the way. What do we need to do? Well, there is a further trick. So the Agda hackers are full of further tricks. The thing that would help would be the following. When I compute the value of this thing and I get this result, I actually know that this equals that, right? But when I'm here, in here, so let's go back now to where we were. So this was just an explanation of why it didn't want to compute. It didn't want to compute, well, it computed the outer one, it just didn't want to compute the inner one. So let's go back to this position where we're stuck. So now we're stuck because Agda didn't compute this one. But what we really want to do is we want to say, look, we computed this and we know that it computed to no P. So there should be a way of saying that this equals that. Because if we had the equation that test keys kk prime equals no P, I could use that equation to convert this bit to no P. If I knew that this is equal to no P, I could convert that to no P, and then it would compute. And then I'd be done. Is there a way to do that? Yes, there is a mechanism in the standard library called inspect. This is deeper magic. If you look at inspect, where is inspect? Well, I'll just put it here. Okay, we need to go, oh, I'll just do it like this. I'll say, what is this inspect business? So this can I go to its definition? No, I doesn't want to go to definition. There we go. This is inspect from the standard library. This is something that you do not necessarily want to understand on the first reading, because the more you look at it, the more ridiculous it looks. So what I'm going to tell you is how to use it. And I recommend that I think you stare at this, and then next time, if anybody is interested, we will actually explain this, okay? Look, I mean, how hard can it be, right? It's like 1, 2, 3, 4, 5, 6, 7. It's just like 8 lines of code. It can't be that hard, okay? They did include a README. No, except they didn't. Who knows where it is? Okay, so the way that you use this is as follows. I will make an additional pattern match where I will ask this inspect to pattern match. And the way that you write it, inspect assumes that you want what is the general case that you would have here? So typically what happens here, you have some function f which you apply to some e, and then you want to know the result. And this is the case here as well. We have some function which is called test keys k, and we're applying it to k prime. And what inspect needs to be told, because it doesn't know what was written here, it needs to be told what the function is and what the argument was. That's what it needs to be told, because it can't look over there. And then you will get an additional result here. And this additional result will be an element of this type, reveal, whose only constructor is square brackets with something inside. So I say, well, okay, sorry, it's square brackets. I keep coming slightly. It just jumped to a random spot. What is going on? So this is going to be something that looks like this. So I have an additional pattern match, which will give me an element that looks like that. Let's see if it works. Did I change this file or something? No? It's taking forever. Ah, no, it's there. Okay, so let's look at what Q is doing. Q is exactly the equation I wanted, you see? I got the equation. So now that I have the equation, I could use subst to replace this. We practice subst, and, right? Where you should, well, you don't have to do that because we also learned rewrite, which will do it for me. So I say use this equation. In this case, what did I get? I obviously don't know how to use Emacs anymore. Wait, now it computed because it did use the equation. So it's just REFL. I think this is enough magic for one day. Ooh, I was fancy. I used Xi. So I don't need it here, and here I'll call it Xi. Just because I can. And apparently I deleted some stuff here. Okay, so that was an explanation. Of course, Danielle prepared an exercise for you where you have to use inspect. Good luck. But Danielle is, I think, from what I hear, he's going to take you through it in a way that it'll be doable. He's good at that. Now, this was rather nasty and complicated, and we use this function extensionality because equality of functions in Agda is silly. So what is really going on? It's a bit unpleasant because we're trying to compare functions, and we're using functions as data. My dictionary is represented as a function, as a piece of data. We normally think of data as something discrete, like a tree. So that's what's going on. But what are some other options? What could I do to avoid this craziness with funnext? Well, okay, first of all, I could use a different implementation, yes? But the other thing I could do is I would say, well, this equation is a little bit too much. So this one says, when I add like this twice, it says you will literally get the exact same thing. But if these are balanced trees or something like that, I might be getting different balanced trees which represent the same dictionary. So it's a little bit too much to say you will get the exact same thing. We should relax this, but what should we relax it to? What we should be saying is not they're the exact same data, organized the exact same way. We should say they carry equivalent information, or to put it in another way, they behave in the same way. We can make the same observations. When we make observations about these two dictionaries, they both behave the same way. That is called observational equivalence. Observational equivalence is a relation which says that two things are equivalent when observed. But what does observed mean? Observed means observed in the relevant way. So what is the relevant way of observing a dictionary? To look up values. So what we really want to say is, these two dictionaries give the same answers when we try to look up things. That would be the better way to define equality in this case. And so that would be an improvement, but then we couldn't use equality. We would have to define a new relation. We would have to, our definition of dictionaries would also have to contain the definition of what does it mean for two dictionaries to be equivalent. And in fact, we already had that in the code. It's down here. It's precisely this thing here. See? It's already saying for every key, they give the same result. So we already used that. We just used funx to get to the real equality. So this funx, this is just cheating. It would be better to just use an appropriately defined equivalence relation. So that would be nicer. But if you go down this road, you get to a place where everything comes equipped with an equivalence relation. So now you suddenly spend 50% of your work fiddling with equivalence relations. Types with equivalence relations are called setoids, and I'm sure that some of you are going to meet them in your projects. They're a nice idea, but there is a reason why they call them the setoid hell. So we're not going to go there today. Working with all those equivalence relations can be a little bit too much. Let's proceed to our next example, which is more of a mathematical nature, and this is monoids. Now this section here is to give you a little bit of a taste of how you would go about formalizing a little piece of mathematics. And some of you expressed interest in the opinion poll, in the poll, to do a little bit of math. So listen to like, this is gonna give you a taste of it. It doesn't have to be like this. This is more like algebra. If you're going to do something that's more like analysis, it'll feel a bit different, but nonetheless, it'll still be math. So let's first remember what a monoid is. A monoid, so how do mathematicians define a monoid? They say a monoid is a triple where you have a set M, and then you have a special element epsilon in M, and you have an operation, and then you have, what happened here? And then you have some laws, namely that the epsilon is the unit for the multiplication, and the multiplication is associative. If we also added inverses, we would get a group. So this is half of a group, or 2/3 of a group. This is how it reads in a math book. But in fact, mathematicians don't say consider the second projection of a monoid. They say consider the unit. So it's not that they think that this is the first, the second, and the third component. They give them names: the carrier, the unit, and the operation or multiplication. So this is not, they say it's a triple. It's not a triple, right? It's a record type. In fact, it's not a triple. It's got 6 things, because they also produced 3 additional axioms, which they are somehow magically not counting. That's because informal mathematics is written in English, and so then you follow the rules of storytelling, not the rules of formalization. So it's not as exact. So let's do it exactly. Let's define a monoid. So what's a monoid? Well, this is the type of all monoids that live in the nth universe. So as you know, there are universes. Each universe has the totality of all the monoids. What is the set of all monoids? Well, this is now describing what one monoid looks like, but its elements then are monoids. So first of all, we have a set. Let's call it M, which is the carrier. Then we have an epsilon, which is an element of M. Then we have multiplication, which is a binary operation, and it's in fixed and left associative. And then there are 3 further fields, which are just the laws for the monoid written down. Okay? Nothing surprising here. There are immediately some useful things which you will discover, that you will eventually discover that you want some other derived notions once you start proving things about monoids. Here they are. Okay, it looks scary, but let's read them. So first of all, maybe this is clearer if I go down here. Let's look at this in the indentation level. So this is indentation level 2 here. So we are still inside the monoid record. This here is still part of the monoid. This is derived. These are derived operations. So what are they? And I'm opening a module just so that I can have open data list. Okay, so the first one is, the first operation takes a list and takes a list of elements and it produces an element. So this is just multiplying all the elements in a list. We have a binary operation, which multiplies 2 of them. We have a unary operation, which multiplies 0 of them. It's called the unit. Yes? But in general, we can multiply a whole list of them. And this is just some fold that works on the list. Fold the operation on the list. Which one? Well, multiplication starting from the unit. So this is just going to go through the list and exactly multiply the elements. Fun story. There are 2 folds because you can start multiplying on the right or you can start multiplying on the left. I suffered about 25% more because I had fold left there yesterday. And then at some point I came to my senses and I changed fold left to fold right, and suddenly 2 lemmas were a lot easier. Okay? So formalization is a lot of fun. This is something that you absolutely you're never going to observe if you're doing things with pen and paper. There's no chance that you will have to think about, am I multiplying the list from the left or the right? It's just not going to come up. So this is fold right? It says, if it's the empty list, then you use the thing you started with. Otherwise, you combine with you multiply with what you have so far and the rest. Okay. And there are 2 properties that we will need of this list. What happens if you multiply a list of elements and this list has the first element and the rest, and then this is going to be the same as the first element and the rest? I'm a little surprised that this is as complicated as it is, but apparently, oh yeah, because I need the, okay. So anyway, these proofs are not that difficult, so I'm going to skip them. I can't do all the proofs here. Too many, okay. But this is the sort of thing that is good to know. If you're multiplying x and then the rest, that's like multiplying x and then the rest. Okay, so here this one, if I'm multiplying 2 concatenated lists, so x's and y's are 2 concatenated lists, I could multiply them separately, like this and like this. And then there are some proofs. The other useful thing is the power, the nth power of x. It's the thing that mathematicians write as, if you have a monoid M, then people write stuff like x to the n, where they mean x times x times x times x and times. And then if you ask them, did you multiply, which way were parentheses? Were they this way or that way? They say it doesn't matter, and they don't want to tell you. Well, when you're formalizing, it matters. You have to pick one. And if you pick the right one, it might be better than if you pick the wrong one or the left one. So it's going to be one of them. Here for some mysterious reason I didn't even use a fold, which probably I could. No, I couldn't. Well, there might be a fold on natural numbers. I just did it with my bare hands. X to the 0 is the unit. X to the successor, it's x times power. Okay, so what matters is whether I put the x on the left or the right. That matters. So the law that we will need later is that, well, this one, x to the m plus n is x to the m times x to the n. Lots of little lemmas that you need to prove, or try to search for them in the library. 20 years from now, the proof assistant will say, hey, why are you bothering with this? I already know this, it's in the library. but somebody has to implement that. And I'm not really sure anybody knows how to implement it at this point in time, to be quite honest. Okay, so those are monoids. We still don't have any examples of the monoids, but let's also do a little bit more math. Monoid morphisms. If I have two monoids, m and n, then I can have a morphism from n to n. What is that? Well, it's a function. Usually you call it f or something, but it's a map. I will literally call it map, okay? So what does this map have to do? Well, map has to preserve the unit, and mapping x dot my is map x dot n map y. In general, when you have any kind of algebraic structure in mathematics, in algebra, you have an algebraic structure. What is a homomorphism? It's a map on the carrier sets that preserves the operations. All of them. Unit, inverse, whatever is there. Let's write that down. Now, mathematicians will say, oh, it's a function. Well, no, it's not really a function. It's a function plus two conditions. So it's a record. A homomorphism is not just a function, just like a monoid is not just a set. So this is going to be another record type. Here it is. And now we have something interesting regarding modules. Okay, so how is this going to work? We are going to define homomorphisms from monoid 1 to monoid 2. Here as input I have monoid 1 and I have monoid 2. But now there will be lots of confusion regarding how do I get to the operation of monoid 1? How do I get to the operation of monoid 2? This is where opening things in a reasonable way is very helpful. I say, open the monoid 1, so give me all the access to monoid 1, but rename stuff. The carrier of monoid 1 should be called M1. The unit should be called unit 1. Multiplication should be called multiplication 1, and so on. And in the second one, I give the 2, 2, 2, 2 there. It looks like lots of working, but you know, it's doable. Now I can actually write down what a monoid morphism is, what a homomorphism is. Well, it's a map which goes from M1 to M2. And it maps epsilon 1 to epsilon 2. And for all xy, it preserves the operation. This is the price you pay to have readable axioms. I don't really know of a better way. I mean, the better way is this. I scribble something on the paper, just like I did here. I didn't explain, it's not really written what m and n are, but you were able to guess. It's not really written what these x and y are, but you were able to guess. You were also able to guess that I mean all these three things, not or, but and so on. This is how humans communicate. We communicate very little, and then we hope that the other person will correctly reconstruct information. Agda and proof assistants are doing their best to reconstruct the information and guess what you meant, but they're not as good as humans in guessing what the other person meant, so you have to write more. Okay, and then there are going to be auxiliary functions. So also for homomorphisms now, we want to say, well, a homomorphism will preserve the product of a list of elements. A homomorphism will preserve powers. So you prove these things. What you should be paying attention to is how are things being developed? Well, there were some auxiliary lemmas. Now I'm dragging these auxiliary lemmas through the homomorphism stuff as well. Did I write this like this? Did I just sit down and write everything top to bottom? Not at all. I only figured out which lemmas I wanted after I tried to do the things that are coming, that are further down below. At some point I said, oh my God, why didn't I prove this lemma before? Because I proved it with bare hands twice. And then I said, oh no, but I should just do it once. So there's lots of this back and forth when you're formalizing mathematics before you figure out how to organize things so that they click. It's worse than doing programming of data structures. It's worse. There's more of guesswork and doing things the wrong way, and then eventually it works out. Okay, now we've already learned the lesson with comparing dictionaries. So let's now do the comparison of homomorphisms the right way. Agda thinks that two homomorphisms are equal when they're equal as elements of this type. So Agda will say two homomorphisms are equal if these two maps are equal and the proofs are equal. That's not something we want. Usually when you say that two homomorphisms are equal, you don't mean to say, by the way, for both of them, we proved in comparable way that they preserve the operation. What does that even mean? So we want immediately to have a good relation, a good equivalence relation that compares homomorphisms. So what would it be? Well, it would be just this, that two homomorphisms f and g are equal when, for all x of whatever type it is, I don't know, like Agda will figure it out. If I apply, what is going on? Yes, let's read this. This is the entire record. So this f, where is f? This f here, it's this f. So this will be easier if I name this. Okay? I want to say when are f and g equal. So I say f and g are equal when something happens. What needs to happen? Well, I want to compare just their maps. So I used open and renaming. I said, open the record f and rename its map to map 1. Open the record g, because g has three things. Open its map to, name its map to map 2. And then say that they need to be equal for all values. So this is another use of open, which is worth seeing how you just, for little things, you do the right kind of open, even if it's just for one line, it makes that line readable. I think it's a good idea. Now that I'm looking at this, I would be actually tempted to call f and g something like f1 and f2 to match the indices. Okay, let's have some homomorphisms. The identity homomorphism goes from a monoid mon to mon. And when you define it, you have to define all three components, but they're all easy. You say the identity map, and then the proofs are easy, so I'm not going to go into that. And then you can also define composition of morphisms. So if I have two homomorphisms, their composition is going to be a homomorphism, and here is the proof. I'm not going to do this. There are some more interesting things that I want to do. And then, by the way, there will be the properties that the identity is the left and the right unit for the composition, and the composition is associative. So can somebody tell me what did I do here? I defined the structure called monoid. I defined the notion of homomorphism. Identity homomorphisms I defined composition, and I showed that the identity is neutral and the composition is associative. What is the structure? No, if I look at all the monoids now, together with their homomorphisms, what do I have? I have objects called monoids. I have morphisms called homomorphisms of monoids. The homomorphisms are equipped with composition and identity satisfying associativity and unit laws. What's that called? A category, right? We really have a category. So we could go one level up and define a record type of what is a category, and then we would show that what we just defined here is, in the grand scheme of things, just one example of a category. So that's definitely one direction that some of the projects could go in, to do something like that. And there is an extensive Agda categories library, which is well organized. So you wouldn't start from scratch. You would do something on top of that library, which is both a blessing and a curse. It's a blessing because you don't have to do things from scratch. It's a curse because it's huge and you have to find things in it. Let's give some examples of monoids. Okay, so here's one example. How do I give an example of a monoid? So one monoid could be natural numbers with addition. So let's do that. Let me do this one. I'll do one. I say, oh, I would like to provide one specific monoid. I say, I will give it this long name. What? Everything's broken. Oh, no, it's not. Now it is. I changed something. Oh, yeah. It's broken because it wants the definition. That's okay, and it doesn't have it. So I say I would like to define a monoid, so I need to give it a name. And so here is the ridiculous name for my monoid. And it's going to be a monoid, and it will be at the 0 universe level. And now I say, Agda, how do I do this? And Agda says, you have to give me all these fields, and I start filling them in. I say, well, the carrier is the natural numbers. The unit is 0. This is addition. And now it's going to get a little nastier. What do I need to prove? For all x equals x. Why is that? Because it already calculated something. And then this one and this one. But I know that Agda nat properties proves a bunch of lemmas, and probably some of them are going to be useful. And then you search from them, and eventually you find the thing that you want, and you use it. And then you say, oh, this is all in the library. That's so cool. Of these, if you actually wanted to prove them, you would only have to work hard for, well, this one you can just do. Probably one of them is super easy. This one is super easy. The next one is just one definition, is one induction. It's doable. You don't want to do it by hand, but it's doable. It's an exercise in axiomatic natural numbers. Here's a similar one, just to show you that a single type can have many monoid structures. So I have the same carrier but different operation, namely multiplication, so it's a different monoid. Here's a third example. The third example is lists. Lists form a monoid because, so if I have lists on some set A, how do they form a monoid? Well, I can concatenate them. So if I have two lists, x1 to xn, I can concatenate them to get a list. And this operation is going to be associative, and it has a unit. Okay, so here it is. The set is the lists of elements of A. The unit is the empty one. Concatenation. Luckily, this data list properties has the lemmas that we need, so we just reuse them. How long will it take you to find these lemmas? I don't know. Takes me about 3 minutes, so I'd say probably more than 3 minutes, unless you've already used some Agda. I've never seen anybody who would be able to just rummage through some huge library of theorems and just find their way around. At least I'm always somewhat confused, but if you're not, then I would like to know, because I'll come and watch what you do. Okay, mathematically speaking, let's do something that is mathematically interesting. Any questions so far about what's going on? Yes?
Any way of searching through the
yes.
library of theorems?
Yes, okay, yes. So okay, so this is definitely a place where we would want improvements. One is Google. Another one is there is an Agda standard library where you get all the modules and you can try your luck. A third one is something that I still haven't fixed in my Emacs, which is Control-C, Control-Z, which is search about. It's supposed to give me all the theorems about a given thing. So if I go here,
well, yeah.
But it's some.
I wanted to ask.
Yeah. But I need to fix it. Sometimes it works, sometimes it doesn't work. Lately, it hasn't been working. And then you say, give me all the currently accessible theorems about plus. And then in a buffer, what you see is a list of things. And you know that you want, for instance, plus has to be, you want something about plus and 0. You get all the theorems about plus, you search for 0. There will be 5 things. You will find the one that you want. Let's do a little bit of math. Okay, I have a suggestion. I would like to do 10 minutes of math now and then have a break, because then we're going to do section 3, if that's okay with you. Okay? So, among all the monoids, some of them are freely generated. What does that mean? What is a freely generated structure? In general, when you have a mathematical structure, you can, what is it? It's going to have some operations, like plus and times and minus, or maybe concatenation or whatnot. And then it's going to have some equations like associativity, unit law. To generate a structure means that you just start with some set of generators, and then you start making elements out of them. But you also need to enforce equations. That is to say, if you just generate them, you will get something that has all the elements, but the equations might not be true. So afterwards, you need to make an equivalence relation that enforces all the equations. And that's called freely generated structure. I explained it in a way that tells you how to make such a structure. But in mathematics, you really want to characterize it. You want to say, when is a structure free? So a free monoid, what is a free monoid? A free monoid is a monoid. So you don't just say it's free. You want to actually say what you really say is a monoid M that is freely generated by some set of generators, say S. How do you do that? What you do is you first explain how these generators, in what sense are these generators elements of your M. So there is really an additional map here called iota. So the data is by S via some map iota from S to M. So the data that you want is this and that. So think of it this way. If you have a vector space, a three-dimensional vector space is freely generated by three vectors. So you might take as your set S the set 1 to 3. And then you would map 1 to the first basis vector, 2 to the second basis vector, and 3 to the third basis vector. So this S does not need to be a subset of M. In general, what you want S to be, S is some indexing of the generators. And then you map the indices to the actual generators. So you give them names so that you want to say, this is the first one, this is the second one. Okay, so now what happens? What does it mean that this thing is generated? It means the following. If I take any other monoid N, then to specify a homomorphism from M to N, it should be enough to specify a map from the generators, right? If I tell you where the basis vectors go, then you know where every other linear combination goes for a linear map. So it's the same here. So I say, if you tell me how to map the generators, then I will be able here to find some homomorphisms. So this has to be a homomorphism. And it will be unique. There will be exactly one way. So without the word freely, you remove unique. Without the more, okay? Then it's at most one. But freely generated means there will be exactly one thing here. Why? Because if everything in M can be obtained from S using the operations, and the homomorphism preserves the operations, I will always be able to get down to the generators, and I know how the generators are mapped. So let's write this in Agda. What does it mean? So I have a monoid M here. See, I have a monoid M. Just to reduce confusion for a moment, I will rename M to carrier because it'll be easier, because I will have two monoids. I have to speak about M and N. Okay, so what does it mean that I have a freely generated module? What does it mean that M is freely generated? I have to give a set of generators. Think of it as indices. Then I have to tell you how the generators are mapped into the carrier of M. Then I have to be able to extend. So what does it extend mean? Extend means given F, you can give me F bar. So this says, given any monoid N, and given any map from the generator to the monoid N, so this is this line here, you can give me a homomorphism from M to N, which is this top thing. But now we want to say unique. Now we know it's there. Oh, we want to say two things. This diagram commutes. To extend means if I start with some generator here and I go here, without the, okay, and then I go down here. That should be the same as going here. That's something I want. So that's, the extension actually extends along iota, says, you see, if I map the extended f on iota of x, I will get f of x. The other thing is uniqueness. Uniqueness, you say it this way, if you have two maps which fit into this diagram, then they're the same morphism. So if I have two maps and both of them fit into the diagram, then they are the same. So records are now being used for all sorts of things, for structures, for homomorphisms, for universal properties, and so on. Do we know any free monoids? The way that you imagine and what a free monoid is the following. If it's freely generated by a set, that means you will be able to write down essentially in just one way every element of the monoid, okay? In some organized fashion, using your operation. I mean, you can always throw in the unit. You can like keep multiplying with the identity, but that doesn't do anything. So you just want up to associativity one way. Okay, so here we go. The natural numbers with addition are generated by 1, because the number n can be written as 1 plus 1 plus 1 plus 1 plus 1 in a unique way up to associativity. But associativity is an equation, so that's okay. Another one is lists. Every list is the concatenation of lists of length 1. Yes. So let's see how these statements are written down. The additive, I say, the additive monoid is free. So I have to specify what are the generators. This is now copatterns. What are the generators for this freeness business? It's the unit type, because there is just one. It's not the number 1. It has to be a type. It cannot be an element. It's a type. It's a type which has just one element. But then iota will map that one element, which I don't even care what it's called, to number 1. And then I need, what else? Oh, how to extend. How do I extend? So extension is just power. Let's think. So if I have the one element type, this is, and then here I have iota, which maps to natural numbers, and it actually takes this thing to 1. It gives number 1. And then I give you here a map into some other monoid M. Well, what is a map from here to here? Essentially, it's an element, right? Okay, how are you going to extend this? You know that 1 must map to this x, because, okay? But if 1 maps to x, then 1 plus 1 plus 1 plus 1 plus 1 has to map to x times x times x times x. So in fact, n equals 1 plus blah 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 plus 1 n times. It has to map to x to the n. So extension is just computing the power. Once you figure this out, the rest is annoying proofs of things. Yes? Here is where the dilemma comes in handy. The homomorphisms preserve powers and so on. I promised 10 minutes. So is there another one? Oh, this is the extend properties. Now there are 2 properties that we need to prove. And this uniqueness business, as you can see, got painful. Okay? It's a little bit painful. You have to prove lots of ridiculous things. Like if you calculate the power, the nth power of n in the additive monoid on natural numbers, well, this is just a very contrived way of saying 1 plus 1 plus 1 plus 1. Will you actually get n? Yes, but you have to prove that. And then here is the proof of uniqueness. And once again, unfortunately, luckily, we don't have the time to go through these proofs, because I know that I very much doubt that everybody in this room has the brain power to follow 10 such proofs in 3 hours. I don't. Another one that is free is lists. And so here, let's just see the definition again. What are the lists generated? Lists on A are generated by the elements of A. In what way? What is this iota? This is the map which takes an element and returns the list of length 1 containing that element. Why is it? Because this is Agda's fancy way of writing lambda x goes to x. See? It's this. X maps to the list which starts with x followed by the empty list, so list of length 1. And then there are some lemmas which are proved down here. And these were also quite painful. And I will think about how I would like to say some things about them because it would be very useful. But I don't have the time, so I will think about it during the break what to do about it. I think that's, yes, so this is what I wanted to say here. So it would be really good to give you some extra advice on how to prove such things. So I need to think about how to solve this problem. If we just throw you to the sharks and give you a project where you have to prove a bunch of lemmas like this, I mean, you're gonna learn to swim, but it might take a long time. So I think it would be good to have some, maybe we'll have some separate sessions doing just this, or maybe I'll record something. I don't know, I have to figure it out. Okay, break, 15 minutes, so 16:27. Okay, so I do have one piece of advice though. How do you find a proof like this? Okay, some complicated proof, or how do you find a proof down here somewhere like this? Okay. I would strongly recommend that you first try to do it on paper. Okay, you really. I will tell you from experience. I was thinking. So this was yesterday. Yes, yesterday. Yesterday I was finishing up these notes, and I was thinking, I can bang this out in Agda. It's just a bunch of question marks, and then I'll fill in the holes, right? And then I think I spent, I don't know, I think I spent 2 hours doing this one down here, okay? It's just 4 freaking lines, okay? 4 hours. Because Agda just has this magical property that it sort of numbs your brain. Your brain says, oh, Agda is taking care of me. I just need to fill in the holes. But, you know, doesn't work that way. So it's a bit like saying, oh, I'm going to travel down some roads and then the junctions will tell me where to go. It's not going to work. So what I would recommend instead, which worked, after a while I followed my own advice and I actually picked up some pen and paper, which is down here, there, and I wrote things on paper. And once I knew what they were on paper, then I knew what my plan was. Then I knew what lemmas I needed, auxiliary lemmas. Then I knew what to search for in the library. But before that, I was just kind of wandering about. And the proof on paper was essentially these lines, okay? And if you look at these lines, you will understand what they're doing. So let's first do the one up here. Even without knowing precisely how things are defined, you will still understand. Okay, this is saying we are using the homomorphism f on some n, and because it's n, it's probably a natural number. Let's hope it's a natural number. And then the next line says, what's changed? You just look at that, what's changed? Well, what changed was that n apparently is equal to the nth power of 1. This is just the business that n equals 1 plus 1 plus 1 plus 1 repeated. And if you look down here, you know, it's actually written this way. Okay, so this one is, see, you can understand how to go from here to there without actually reading any of this stuff here. That's the purpose of these proofs, is that you're writing down the intermediate steps, because often you can just tell, yeah, we can get from one to the other, and if I need to know, this is how it's written. And so if you follow this, this is now what is this is exchanging f and power. You see, here it's f of power. But here it's some other power, which is presumably in some other monoid, and f. And some funny stuff. But the important thing is it's exchanging them. So this is very likely something about how homomorphisms exchange powers. And this is a lot easier to see on paper than when you're in the middle of Agda. It's a lot easier to see that that's what you want to do. And then here I switched from, here I use the actual hypothesis they here have somehow it switched from F to G, which is probably good. And then the story repeats itself. Or down here, if we look at down here, okay, so can we follow at least some of these, okay? So this is saying we're mapping in some monoid some homomorphism on lists. And then the next line says, this is the same as mapping this F business on the list of length 1. See, this is the list that is composed with X followed by some list of X's. And the next step says, hey, you could just use F on the list of length 1 and then multiply that by using F on the list of X's. And these steps, even without knowing the precise definitions or what they mean, you see the algebraic content in them. You see that I am just using the fact that F is a homomorphism, and so when I map over the lists, if I it preserves the operation, so I take things out and so on. And then here, the only thing that happened was that F switched to G. But if F switched to G, there must have been some assumptions about F and G, and these are precisely the assumptions you want, and then you go back. So my advice would be really try to understand as much as you can what this is mathematically speaking on paper, and only then try to hack it out. Don't just try to hack it out. You can kind of hack things with the data structures when you do dictionaries and trees. Then you can kind of hack them out because there the math is not yet at all fancy. It's more like combinatorial. You know, I have 3 cases to consider or 4 cases to consider because I'm pivoting trees this way or that way. But you still have to understand that there are 4 cases to consider, and then there something else is difficult. There you typically need to figure out what is the correct induction hypothesis that will get you recursively through your data structure. So there the point is not so much in figuring the steps of reasoning, like here, but rather figuring out the exact induction thing that you need to formulate so that you can then actually carry out the induction. But once you've got the right one, usually then it works. Then it just goes zoop and it works. But it's difficult to figure out what it is that you want to prove. In mathematical theorems, it is more often the case that you know what you need to prove. You know that there will be some reasoning steps like I need to get from this side of equality to that side of equality, but you don't know how. Inside the proof, you don't know how. Anyhow, let's do this last part, whose purpose also is to teach you something new and interesting, which is monads. Has anybody explained monads to you so far? Nope. How many people have read a blog post about monads? Okay, close to 0. Now, this is a fascinating piece of mathematics for somebody who is interested in the use of mathematics in theoretical computer science and more specifically in programming. One thing that distinguishes programming in general from ordinary math is that a program is more than just a function. It's more than just a mathematical function. Because when you have a function in a programming language, it can do all sorts of things that mathematical functions don't do. For instance, it can have a secret counter. So every time that you call it, it gives you a different result, even though you called it with the same argument. It can print things out. You call the function, it asks the user to input a number, then returns that number. Good luck figuring out what the function is doing. So it can do all sorts of crazy things. These sorts of crazy things are generally called computational effects. And there are lots and lots of them. For instance, non-termination is a computational effect. A mathematical function will give you will produce you a result. A piece of computer code can leave you hanging and waiting, and you're waiting and waiting and waiting, but you don't know. Maybe tomorrow it will return a result. So this is a computational effect. And I/O is another one. Input, output. Anything regard, or any kind of interaction with external environment. But then also phenomena that happen strictly within a programming language can be thought of as computational effects. One is exceptions, for instance. When an exception happens, such as division by zero, or the user threw an exception, or index out of bounds exception, those are things which they affect the control flow. They affect the overall execution of the program so that the control goes to some random place somewhere else. It doesn't follow the discipline of calling functions and returning results. That's another one. Another one is non-determinism. Non-determinism, there are various kinds, but the non-determinism means that the behavior is not strictly specified by the program, but maybe there's some randomness involved, or maybe there are multiple choices. If there are multiple possible steps, for instance, how could you have multiple possible steps? Maybe the way that you're programming in your programming language doesn't specify exactly how things should happen in the parallel components of the processor. And you say, oh, I allow the program to run in some undetermined fashion in parallel several things, and whatever happens, happens. And under these circumstances, the result that you get might be one of possible results, but there might be many possible results now, because it will depend on exactly how the different pieces interleaved in parallel, and that could affect the final result. So that's non-determinism. There is probabilistic non-determinism, where you do things with certain probabilities and then things happen. So what is amazing is that all these things have a common mathematical structure, which is called monads. What is even more amazing is that this was discovered and popularized first by Eugenio Moggi in 1985, something like that. But the monads themselves were invented in the 1950s by somebody who was studying homological algebra. Okay? So this is a rather strange, amazing connection. This direction has many possible projects. You could orient yourself more towards the programming language aspects of it, which could be more mathematical, in which case you would be looking at formalization of the mathematical properties of monads, but there are possibilities here. Also, this is sort of this is very close, or is part of the core research and expertise, both of Daniel and myself, but more Daniel than me. So he can offer really good advice on this topic. Okay, but what is it? Okay, what is this common thing? Okay, so the common idea is that first of all, we are going to differentiate computation from value. Value is a pure piece of data. There is nothing to compute. It's just bits of information. They cannot be executed. They're already in their final form. Something like a list of numbers, or just a number, or a tree, things like that. Also, a function is data. A function by itself does nothing. Before it does anything, you have to apply it, and then you trigger some process that will do something. But a function by itself is also a value. It doesn't do anything. You have to first call it before it does anything. Okay, so a computation, on the other hand, is some more elaborate thing that can trigger various computational effects. So it's something that we still need to process. It's something that is active, and it's going to be processed, and it's going to turn the wheels, and something will happen. One of the things that can happen is that it will successfully complete and give you a final value. But it need not. it may raise an exception and give you no values. It may give you 5 values if it's a non-deterministic computation. It may give you many, or it may give you one randomly, or it may give you a probability distribution of values because it's a probabilistic computation. So these computations are more complex objects that are not pure data, but there's something else about them. So another one, by the way, is stateful computation, something like a finite state automaton or memory, where you can change the state of the memory. So maybe a computation actually is a value together with state, and then the state can change, things like that. Okay. Now, the idea is that we're going to do the following. We're going to have a data type A, type of values, but then computations will be represented by some other type that I'm going to call T of A. And this one is supposed to represent what the computation is about. So in particular, it has to account for possible effects. So what are some examples? Okay, so there is a trivial example. That means no effects. Everything is a pure computation. This is usually not, you usually can't write entire programs this way, but there could be very useful pieces of code, little pieces of code, which happens to be pure. And if you can tell that they are pure, that's very good, because you can do lots of optimizations when you're sure that it's pure, where you're sure you know that no effects can happen, you can reorder whatever you like, you can compute it several times if you want to, you can cache it, you can do whatever you want with it. So this is good. Okay, so what's another one? So another one would be, suppose we want to say there can be an error. So it's a computation, but for various reasons, such as division by 0 or something, it can crash. So that would be 1 plus A, or just even better, maybe A. Because you think of this, if we get this, it's error. But if we get that, it means we successfully computed and it's a value. Yep. You see where this is going? I'm making this T of A more complex so that it also encodes the things that are going on with the computation. So if the computation can just suddenly stop with an error, then what I will get is this. Another one would be something like state. Okay, well, I want to mention state. I don't want to mention state right now. So here's another one that I'm going to actually implement, is sometimes you have a computation, but what you're doing depends on some global configuration. You know, you run your program and it wants to read configuration from some file. It's read-only configuration. So it's like having global read-only values, and you want to consult them, like command line options, some flags telling you what to do. Okay, what is that? The point is that the configuration file, it's not part of your source code. If it were just part of your source code, then this is just a bunch of definitions of variables. You know, you just say, you know, verbose output equals true, blah 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 blah. No, I'm thinking only once I started to run, only once I ran the program, the configuration is going to come from somewhere. So it's like read-only state. Well, that's going to be like this. So this is global read-only state, or in other words, think of it as configuration, config data. Something that your program at runtime, it's told what the parameters are. So you pass it the parameters, and then you actually get the result. Okay, so another one is, so this one is called the reader monad. because you read the configuration. You can only read it, you can't set it. Another one would be the writer monad, which writes things out. This is going to be in the exercises, so I'm not going to do that one. But here's one. How would you say that you can return multiple results, that more than one result is possible? What do you actually return then? Well, a list of results, right? If you allow empty lists, so that just also means 0 results. So you think of this as multiple results. And this is also called this is one kind of non-determinism. Non-determinism means the result is not uniquely determined. There are many kinds of non-determinism. This is one possibility. You could think of another one, like finite probabilistic distribution on A. And then you will get probabilistic things. There's lots and lots and lots of them. There's an industry of these things. But what do they all share in common? So what they all share in common is you have this T, okay, which takes values, what the type of values is, and then it gives you another type which explains what the computations look like. Yes? Every one of them, yes, had the type of results. Okay, there's another one which is called eta. Eta is something that, so this is eta at A, okay? It goes from A to T of A. And this one tells you how to embed a value as a pure computation. Okay, so let's do some etas. So for exceptions, so if T of A is 1 plus A from above, then eta at A is just. Well, let me write here this one as maybe A. This is just X. This is the exception monad, exceptions. Right? If I want a computation which doesn't, I want a computation which returns the value X, and it doesn't die with an error. Well, then that's just X. Or what if I have lists? And I want to say, okay, the general case is that my computation is actually doing several results. But which of these possibilities is the one that expresses the fact that I have exactly one possible result? It's the singleton list. Yes? When you get a list, you will get a list of possible results. What do we consider to be the pure information? The pure information which is deterministic is to have exactly one result, and that is a list of length 1. So this is the list monad. How about readers? So I want to say, I don't care what the configuration is. I'm going to ignore the configuration and just immediately return the result X. I will return something that doesn't depend on my configuration. That is the pure computation which ignores its read-only state. Well, that's going to be lambda. Ignore this, just give me X. So that's the second component. The first component was this operation which transforms pure values to types that express how what the computation is packed. What is the type that represents the possibilities of my computation? Okay. The third one is, well, what's missing? What is really missing at this point is, how do we combine computations? If I have two computations, how do I combine them? So that's another one. This one is called bind. And in Haskell, for ridiculous reasons, it's called this. Maybe the reasons are not ridiculous. It kind of looks nice, okay? It's this operator, but I will call it bind on paper. So how does this work? Okay, the way that bind works is this. I want to combine two computations. Well, the Naive way would be, okay, I have one computation, I have another computation, and I want to combine them into some third computation. Well, no, there has to be some interaction between the first and the second computation. They cannot just randomly combine two totally unrelated computations. That's silly. So instead, what I want to say is, I have a computation that I want to perform. This computation will produce some result. Then I want to feed the result into a second computation. This computation may or may not produce a value, or it may produce many values, or it may do something with the state and produce a value. Whatever happens, if and when I get one of these values, and maybe I'll get many and I have to combine them all, I take the value and I continue with some other computation. The result should be a computation which returns a B. Yes? That's the third component. Now, this component, let's look at some examples. So if I have the exception monad, what will the bind look like? Well, it's going to be from maybe A to maybe B to maybe B. Now we have to do something reasonable. Well, what could this first computation do? It could give me a value, and then I will get just X. And then what do I do? If the first computation does produce a value, then I want to continue with the second computation using this. Well, I will just do f of x here. But I shouldn't, right? Whatever happens. So this is the case where I first do something, I succeed. How do I continue? Well, by just continuing. But what if the first one raises an error? What can I do? So my first computation aborts. Well, then the whole program should abort. So the result is nothing. I don't even try to run the rest if I get a problem, if there's a problem. I don't even try to run it. How about lists? What will this bind business do? Okay, it'll take a list of A's. So it takes many results. Then it gets a function which, for each possible result that I could get, it continues and produces even more results of type B. But at the end, I have to give a single type, a single list. What will this do? So think of it this way. I get several results here. I can feed each result into a function. If I feed one of them into this function, I will get possible results. How do I combine them all?
You map across.
Okay, so let's see. If I map f across the x's, then I will have a list of lists of possible results, because each x here will give me a list of results. So now I have a list of lists of results, but I need a single list.
Can't you fold?
Yeah, except it's not called fold, it's called concat. But what you probably mean is you just put them all together. Yeah, you fold concatenation. Yeah, so it's called concat. Okay, but that's what you do. And that is the reasonable answer. Okay? So what are we doing? Let's stop to think. What we're doing is we are describing mathematically, or maybe you can say we're describing using pure functional programming, how to simulate computational effects. These are not real computational effects. A real error, yes, will make the computer produce some smoke. That's a real error, yes? But this is a simulated error. It's a software error. Real non-determinism is not going to produce a list of results. Real non-determinism will spawn several universes in parallel, each of which is going to give me a result. And then those will further spawn more parallel universes. That's real non-determinism. But here we are mathematically modeling these phenomena. There are also some laws. We're not done. There are laws. there are laws which say what happens. For instance, one law that you would expect is that if you pass this function a pure value, so if you bind a pure thing, I have a pure computation which immediately just returns the result x, and I combine this with some further computation which expects a result. Well, that should be the same as just doing this. And there are two more laws, which we are going to copy from Agda. So let's read this. Okay, so first of all, we have an operation T, which encodes what sort of computation we have. What is it carries, T of A carries the information needed to represent a computation with of a certain kind, like non-deterministic or state or whatnot. Then the eta business is about pure computation. So given any value, pure value x, I need to be able to encode that value as a pure computation which immediately returns just precisely that result. And so that's called unit of the monad, the unit monad, the monad. And then there is bind, and it's here, you see? It says, take some computation of type T of x, take a function which wants a pure result, after which it will do a computation of type y, and then when you combine these together, you will get something that is a computation that returns a y. Monad laws. Here was the first one. If I feed a pure thing into f, that's the same as f of x. Here's another one. Let's see if we can understand this. Okay, so this one says, if you perform a computation, and then you follow by the computation that just returns the result. That's silly. You could just do the original computation. There is nothing is gained by combining a computation afterwards saying, oh, and any result that we get is the result that we get. That doesn't do anything. Yes? The third one is associativity. It's how to combine. If I first combine, so I take a computation C, I combine it with another computation F, then I combine it with some computation G. That's the same thing as combining C with what? Well, combining C with something that takes the result, feeds it into the first computation, and then does the third computation. So when you think about these laws, you see that they are not unreasonable. And what is more, all of these examples up here are examples of such a thing. This is a common structure that is common to all kinds of computational effects that people have come up with. So this is very nice to know. And in the formalization, in Haskell, you get this much. And then in Haskell, because Haskell uses the monads, you get this much, and then this is written down in the comments, and the compiler knows something about it, and they have some support for it. But with dependent types, you actually write it down. So then if somebody wants to implement a monad, they have to actually verify these things. I have two examples here. One is the reader monad. So let's try to understand what it does. So the reader, so parts of it we already did, okay? So how do I represent computations that return values of type X? It's functions. Why? Because it will first ask, hey, give me the global configuration, so an element of R, and then it will produce the result. So that's my T. It's like before. And then what is the pure computation? A pure computation returning X will read the global configuration, but then it'll just return X. It doesn't need R. So I could put underscore here. Okay, how do we combine? Oh, this is funny. Okay, so this is the first one that's interesting. We have here a computation C, and this computation C, before it does anything, we have to give it the global configuration. And then we have this F, which will take the result, and then it will want the configuration. So how does this work? Okay, it works like this. First, you compute C. How do you compute C? You run C by giving it the global configuration R, and it will produce a result. And then you will give this result to F. And what f will say, it'll say, okay, but I also want the global state, and so you give it the global state. What this is just a very, okay, so what is this in terms of functional programming? I have some value r, and I want my entire program to have access to the value r. How do you have a value r that everybody in the program can access? Option 1, you have a global variable. But that's not going to work if your value is coming only at runtime. If it will be given to you after you have compiled the program, then it has to come from somewhere else. Where will it be? Well, it will be stored somewhere in the memory. Okay? And then you read the memory. So in fact, there should be an operation that reads the memory. It's down here. In Haskell, it's called ask, so we'll call it ask. If your global configuration is R, then you say, well, it's R. It's the identity function. It's kind of funny, okay? But this is the operation that reads memory. This is the state of my read-only memory, and it returns it. Here's another one. It's lists, okay? Let's just verify that it's the same. It really is concat map f of x. See, it's concat map f of xs, just like what you said. And then this is the unit list. And then the rest is some nasty equational reasoning, which I hoped I would be able to explain today, but apparently not. And I have to solve the problem because at least everybody who is going to work with data structures will want to know more. Tomorrow's exercises will make you do similar things, but they will be easier to do than the ones that are here for lists. This is maybe not, you have to think about how to get through these steps. So maybe I'll do this next week or something. But I do want to cover some of this. What else? Oh, this is one last thing. Haskell and also Agda has a nice notation. First of all, programmers think that eta should be called return because it just returns a value. Okay? So we have this inside our definition of a monad. I have here just as part of the record, return equals eta. Okay? So just for convenience. Okay, but then the other piece of information, the other piece is when you write programs in this style, you keep doing the following. You say C, and then you do the funny operator, and then you write lambda x, and then you do some other C prime. So what does this mean? This means perform the calculation C. Once you get the result, pass it into X and do it and then give it to C prime. And it gets worse because these things get nested, so you end up writing stuff like this. And then you say, well, and then C prime is going to do afterwards something else. It'll give you a Y, and then you will be doing C double prime, and it keeps going. And you get these super annoying nested things. So there is a better way, and the notation is that this thing here is written as do, and then you say X becomes C, and then you do C prime. Or, when it's nested, it becomes this. Do, and you say X, C, Y, C prime, and then you keep going. So C double prime now. But you can keep going like that. And you can also just ignore a result. So maybe you write it like this. I say, I just want this one for its effects. I don't care what the result is. It'll have some effects, but I don't care what the results are. So this you can also do, and you don't have to do it like this. You can just, this one you can simplify to just writing C prime, like that. That just means I don't care what the result is. Okay. So then Agda has the support for this. It'll do it for you. It'll translate. So then the programs start to look like Fortran or Java or Python Fortrans. programs. So here's one. You say, oh, this one should be returned. I'm very sorry, because we're doing programming. Okay. So you say, first, which monad is this? This is the reader monad. It says, first, let x be 5. So x, this is the result of the computation that immediately returns 5. Y reads the global configuration. Then we return x plus y. So you can write stuff like this, and it's more readable. And it looks like procedural programming. Here's another one with lists. So you say, let x be one of these non-deterministic results. So x is one of 3 possible results. Let y be one of 2 possible results. Then we return 10 times x plus y. So if you ask what happens here, I don't know of a better way than that. And you say, what is the result? What is this demo 2? It says it's the list of all possible results. So 14, 15, 24, 25, 35, 34. It combines all these concats, maps, everything. It just goes into play. It goes. But the thing is that's written here looks a bit like some sort of weird procedural programming where you have the effect that you can return many results. Yes? Okay, it's probably past time. Yes, it's past time, so I should stop here. Thank you. In the exercises, you will combine monads. Okay, so I can say one sentence. The monad that you will do tomorrow is output monad. Here is what output is. On the screen, you already have the stuff that has been printed. How do you print more? Well, you say something like write or print. Okay? What happens? The thing that is already on the screen is multiplied by the thing that you printed, where multiply means concatenate strings. But it doesn't have to be concatenate strings. In fact, you could be outputting anything so long as you can multiply 2 things together. So the writer monad will be using general monoids. Okay. So that's exercises. Please have a look at the notes. There are various other pointers and so on.